Bismillah ar-Rahman ar-Rahim. We are still giving more and more examples as applications for Newton's second law. Now we will proceed to example number 5. Okay. Example number 5. In this example, we have a passenger in an elevator. So let me draw the elevator. This is the elevator. And we have a person standing on a balance scale. Okay, I don't know why he's doing like that, but this is the question. Okay, so here we have a balance scale, and the passenger is standing on that scale. The mass of this passenger, is a little bit in the heavy side. Is 100 kilograms, just to make it easy for calculations. And we would like to ask about the reading of the scale. Okay, find the reading of the scale. Okay, sometimes we can replace this, the reading of the scale, we can replace it with the normal force, because the scale will be reading the normal force. In fact, when you stand over the scale to find your weight, it doesn't read your weight always. Sometimes, as we'll see in this example, actually it reads the normal force, and this normal force will be changing as the elevator changing. Okay, so he might ask you find the normal force. Okay, the normal force on the person, or sometimes we can write it as find the force exerted on the passenger. This is just the definition of the normal force. The force exerted on the passenger by the floor, or the scale in this case, by the floor. Okay? Now we'll have different cases. This is the statement of the problem, but we will try to find it in different cases. Let me start with case A. Case A, find this reading when the elevator is either the elevator is moving up at constant speed. This is the first case. Or similarly, the object is moving down at constant speed, or even if the elevator is at rest, doesn't move at all, okay, is at rest. What is common about these three situations? If the object is moving up at constant speed, moving down at constant speed, or at rest, okay, if you remember from the kinematics, this means that the acceleration is equal to how much? Guess, my student? Yes, true. Acceleration is 0. Okay, in all these three cases. Okay, so how to find the normal force when the acceleration is equal to 0? Meaning that moving up at constant speed, moving down at constant speed, or even the elevator is at rest. Okay, we will start as usual by drawing the free body diagram. What is my object of interest? In this case, the normal force is applied on which object? It is applied on the passenger. Okay, so my object of interest is the passenger. The elevator is not my object of interest. Okay, my interest doesn't go to the scale. My object of interest is the passenger. So I'll take the passenger, I'll draw him as this little circle. Okay, what are the forces acting on this passenger? The forces are, we know Fg is downward, and Fg is nothing but mg. This is its magnitude, its direction is vertically downward. And there is a force which is the normal force, which is the force exerted by the floor or the scale on the passenger. Okay? And in this case, the acceleration is equal to 0. Now, I am ready to apply Newton's second law. What does it say? It says F net equals ma. The acceleration is 0, so this is 0. What are the forces present on the passenger? We have Fn upward, mg is downward, this is why I give it minus, and this is equal to 0. So Fn is equal to mg, okay? And the mass is 100 kilograms multiplied by 9.8, so you will end up with 980 newtons. As you can see here, this is the normal force is the same as the weight of the person. Okay, so Fn in this case will be equal to the weight of the passenger. Okay, so you will get your actual weight if you measure or if you stand on the scale in non-accelerating frame. Okay, so you have in the elevator while it is not moving at rest, or the elevator is moving down at constant speed or moving up at constant speed. Okay, let us go to second part of this question. Part B. If the elevator has an acceleration A equals 1 meter per second square. This is the magnitude of the acceleration, and the direction is upward. Okay? We want to find what is the normal force on the passenger in this case. Okay, first step is to draw the free body diagram as usual. So this is the person. Okay, but before, let me explain, my dear student, what do we mean by the acceleration is 1 meter per second square upward? When can we have this acceleration? This acceleration can be achieved, or we can think of it two cases or two situations. First of all, the elevator is moving up. Elevator moves upward. Okay, so the velocity is upward. Okay, and the speed or with increasing speed. Okay, so the velocity is upward and the acceleration is upward, and you will have the speed increasing with time. Okay, so this is one situation. The second situation, if we can have the elevator moving downward, okay, so the velocity is downward, okay, and if the acceleration is upward, what will happen to the speed of this elevator? It will be decreasing. Okay, so this is the second case of having upward acceleration. So elevator moves downward. Of course, it should be moving straight or vertically downward. The elevators are moving in. So the elevator moves downward with decreasing speed. Okay, so in these two situations, the acceleration is upward. One of them, the speed is increasing and the motion is upward, or the speed is decreasing and the motion is downward. So let me draw the free body diagram. In both cases, whether the motion is upward or the motion is downward, the free body diagram will look like the following. So I have, this is the person, the passenger, okay? The forces acting on it are Fg, which is downward. It has a magnitude of mg. And the normal force, which would like to calculate here. And the acceleration is upward, okay? According to the statement of the problem. Now I am ready to apply Newton's second law. on this object. It is one-dimensional problem, so I'll apply it along this vertical axis. So F net equals MA. Okay, let me now, on the left-hand side, I'll plug in all the forces acting on my object. I have Fn upward, so it is positive because it is upward, minus mg. I put the minus sign because it is downward. Now I am done with the forces, equal. Okay, and the left-hand side, I should plug all the forces. Okay, when you are done, put the equal sign, then you go to the right-hand side where you put the acceleration with its sign. So the acceleration in this case is upward, and my upward is positive in my case, so equals ma. Okay, so now I can write Fn, the normal force, will be m multiplied by g plus a. If you plug in the numbers, this is 100 multiplied by 9.8 plus 1, which is 10.8. Okay, so this is 10.8, and you are left with normal force equals 1080 newtons. As you can see here, the normal force is greater than the weight of the passenger. The weight of the passenger was 980 newtons. Now, the normal force is greater than the weight of passenger. Okay, we sometimes call it the apparent weight. Okay, so this is not your actual weight. You will see this apparent weight in the case of yes, and you can feel it when the elevator is accelerating upward. Okay, you can feel there's too much push on your back. You feel it in your back and on your legs in the elevator. Okay, you feel this increase in the normal force or the push of the accelerator on your body. Okay, let us get to the third case, which is case C. You guess here. Here the acceleration was 0. In part B, the acceleration was upward. So you can have a correct guess in part C that the elevator will be accelerating if the elevator has an acceleration of magnitude A equals 1 meter per second square. This is the magnitude, and the direction is downward. Okay, so it is similar to the previous problem, but now the acceleration, same magnitude, but it is downward. When can we have such a situation? We might think of the elevator moving up, the elevator. Let me choose the other pen. The elevator moves downward, okay? Okay, and the acceleration is downward. So the velocity is downward and the acceleration is downward. This means the speed is increasing. Let me use the same wording, with increasing speed. With increasing speed. So it is accelerating downward. Or the second case, we may think of my elevator moving upward. The elevator moves upward. I hope it is clear. Upward. But what will happen now? The velocity is upward, the acceleration is downward. So what happens to the speed of my object? Yes, it is decreasing. So with decreasing speed. Okay? Both situations, the acceleration will be downward. If we draw, as is always the case, we start by drawing the free body diagram. This is my passenger, okay? And what are the forces acting on the passenger? I have Fg downward, which is the mass of the passenger multiplied by g, and the normal force, which is upward, and the acceleration is downward in this case. Okay? Now, We apply Newton's second law in this one-dimensional motion, vertical motion. F net equals ma. This is the general form of Newton's second law. What are the forces? I have the normal force upward, which is positive, the gravitational force, which is downward. This is why I put it negative. I am done with the forces. Now I go to the right-hand side, which talks about the acceleration. So mass multiplied by acceleration, but my acceleration is downward, okay? But downward, I've chosen that direction to be negative, okay? So this will be minus ma, okay? So we can write that Fn will be m multiplied by g minus a. G is 9.8 minus 1, so this is 8.8 multiplied by 100, so you are left with 880 newtons as the magnitude of the normal force. But you notice this is less than the actual weight of the passenger. The actual weight is 980, but in this case, the normal force or the push of the elevator on the passenger will be less than the weight of passenger. And I think you felt this when you are in an elevator and the elevator is accelerating downward, okay, at the start of the motion of the elevator, accelerating downward, you feel yourself lighter than, or you feel less push from the ground or the floor of the elevator. I hope with this question you have a broader understanding of the meaning of the normal force. The normal force is the push of the surface on object standing on it or supported by these surfaces. Also very important to know that the reading of the scale when you stand on top of it, the reading of it is the normal force, okay? And this normal force will be changing depending on the magnitude of the acceleration, okay? If the acceleration is 0, okay, in these three situations, the reading of the scale will be the same as your weight. If the acceleration is upward, the normal force will be greater than the weight. And if the acceleration is downward, the normal force will be less than the actual weight. Thank you.